This is the fifth video for the final exam review. Unit 5 for us was electrostatics. Kind of had two different issues in there. We were looking at forces and fields, and we were also looking at energy and voltage, and kind of just separating those two issues onto either half of the page here. For forces and for fields, those issues were both vectors, and that's when you had to use your head to figure out which way the direction would go. And you have to be super careful on this one because some of the time, not all the time, but some of the time, these questions were actually two-dimensional, and you had to go and treat them with, Pythagoras and trigonometry and that sort of thing. They didn't always have that, but often they did. On the other side of the page, we're looking at energy, potential energy, and the pre-calculation of that, which is voltage. The good news here is you can totally trust the math, and just put the plus or minuses in and everything is actually okay. Stranded in the middle is the equation for parallel plates. It's actually got some part of that equation which talks about electric field, which was from the first half of the chapter. And then there's another part of the equation, voltage, which actually relates to the second half of the chapter. Another little issue with parallel plates, that one equation there, E equals V over D, is only for parallel plates. And F equals ma being used to figure out accelerations and then velocities can be done for parallel plates. You can go ahead and use it for this part of the chapter, but not for forces and field questions or energy and voltage questions where things are moving around with point charges. Let's try this out. First question here, trying to decide each time as I look at these whether it's a force and field question or whether it's a voltage and potential energy question or maybe parallel plates. Electron is accelerated from rest using parallel plates. Okay, there it is. It's parallel plates that have a potential difference of 840 volts. As soon as I see that 840 volts, I'm thinking of that. I know it says volts, but I'm thinking of that as being joules of energy per coulomb, because that's what voltage is all about. It's pre-calculation. And this potential difference, another name for potential is voltage. Okay, those are one and the same. Either potential or voltage can be interchanged. And you're trying to find the velocity of the electron after it's gone from one plate to another. The picture might look something like this. Maybe we've got one plate here. Maybe it's negatively charged with a battery. And there's an electron, doesn't want to hang around near that. And it's actually going to want to get towards a plate that's positive. And there might even be a little hole in the plate that we can use to launch the electron through. But if this plate is positive, then it's definitely going to want to leave that negative plate and head towards the positive one. I'm going to just talk about two different ways to do this. I'm not even going to give you the actual answer to this because I don't really care. It's more just reviewing the ideas. The best way to actually approach this question is to look at it from the point of view of energy. I would do this question by saying potential energy is going to get converted to kinetic energy. That voltage, 840 volts, is not quite energy, but it will be if you multiply it by the Q for the electron, the elementary charge. So for parallel plate questions where you're launching particles, QV is equal to 1/2 m velocity squared. That is the best way to go. It's super quick, and as long as you're going from plate to plate, that works awesome. That'll tell you exactly how fast that electron is going. When it gets to this other plate here, maybe comes through the hole and is flying out with some speed, that will definitely tell you for sure the velocity the fastest way you can. There is a slow way that you can get there. I would not do this unless there's something that forced me to do it, but the really, really slow way to do this would be to first go and find out what the electric field is by doing voltage and dividing by gap size if you knew it, and in our question we didn't. Second thing you could do is you could say, okay, well, how about we go and find the force on that electron by going QE? So you could take your answer from the electric field from part 1, put it in there and find the force. And then third, once you know the force, you could go F equals ma. You could take your answer for force, put it into F equals ma and find the A. And then finally, you could do some kinematics. And if it started from rest, Vf squared would equal 2AD. And you could take that A and you could put it in here. Wow, really long way there. I wouldn't do that unless you had to. As if they maybe said, oh, we're only going to go halfway from plate to plate, then maybe I would do that. But generally we avoid that. Part B, if the acceleration of that electron is that kind of awkward number there, 3.513, 10 to the 15 meters per second squared, how far apart are these plates? So we never did know, back in part A, what the separation distance was, which meant that you couldn't even do that one the slow way. But now that they're giving us an acceleration, maybe we can use this slow way idea to figure out what that separation actually is. So I guess maybe part B is a situation where you're forced to do it the slow way to some extent. You could go and do F equals ma. You could figure out exactly how much force there is acting on that electron. We could put in our mass, 9.11, 10 to the negative 31 for an electron. You could put in that number they've given us for the acceleration. And it turns out the force that's acting on that electron is 3.2 times 10 to the negative 15 newtons. And just pointing out, it is, in this situation, okay to do F equals ma. We're not playing around with point charges getting closer or farther from each other. Parallel plates has nice uniform acceleration, so this is okay. Once you know that value for the force, then you could go and say, well, wait a minute, the electric field would be the force divided by the Q that was involved. So the electric field would be 3.2, 10 to the negative 15, all on top of the Q, which is the electron's Q, 1.6, 10 to the negative 19. Notice I'm not even bothering putting in the negative charge. And you find that the electric field is 20,000. You can call that newtons per coulomb, or if you want, it's exactly the same thing to say, hey, that's also just like volts per meter, which is kind of where we're going next. And then we could go to the equation for parallel plates. The electric field that we've just calculated must have been the voltage divided by the gap. So 20,000 is equal to 840 volts divided by some gap size. So that would be a situation where all those slow way calculations put together, might have to be done. We don't know what the gap size is, and somebody really wants to find out. Okay, great. We can go at it that way. Question 2 on the review is probably the ugliest question on this set of 4 pages. It's a bit over the top, to be honest, to be actually moving around from point A to point B and having 2 different Qs at the same time. Usually the questions have one of those situations or the other, and we're going to talk about what it would look like if it was just a bit simpler once we've got the page kind of done. But we'll start off going for the whole thing. So there are a couple of point charges, Q1 and Q2. They're glued down. And then there are these 2 places in space, A and B, and the dimensions are all nicely there. And eventually, if you look down in part B, we're going to be moving an electron from A to B. We don't know about it yet, but it is true. There is going to be a need to move an electron from location A over to location B. That comes later, though. Part A, we're going to try to find the potential difference between locations A and B. Okay, potential. Same thing as voltage. Trying to find the voltage difference between A and B. Ultimately, we're going to say, yep, that voltage difference, it's the voltage at one place, let's go final, minus the voltage at the other. To find the voltage at either spot, you have to do what we call superposition. You have to add together the individual voltages. But the good news is, this is done with just adding together plus or minus values, scalars. There's no vector involved here. So the voltage total at A is going to be 2 separate voltages. I'm going to go K, and then I'm going to grab that first Q, that positive 3.5 times 10 to the negative 6, and I'm going to divide by how far away A is from that Q. Nothing gets squared when you do voltage, just a 1.4. And then I'm going to add on, this is superposition, I'm going to add on the other voltage, K, the negative 2.4, 10 to the negative 6, all divided by how far this charge is away from A. Well, that's 1.4 and 1.6. That's 3 meters away. I ran those numbers ahead of time, and I found that that was 15,300 volts. The voltage at B, also superposition, we would be going K. It looks almost identical. Positive 3.5, 10 to the negative 6. All divided by, okay, well now how far is B away from Q1? That'll be 3 meters. and then we superimpose, we add on the other voltage, negative 2.4, 10 to the negative 6, all over the distance here, 1.4. Okay, I ran those numbers ahead of time. They are totaling up to negative 4,900 volts. Now, in a second, we're going to subtract because you were asked to find the difference in voltage. But before we do that, this superposition idea is all about this addition that we had to do to find the individual voltages. Then we can go and work with this question where they're saying, okay, can you go and find the voltage difference? Sure, yeah, differences are all about subtracting. So you want to talk about voltage difference. Difference in voltage would be the final. I'm going to call B the final. Negative 4,900, subtract because I'm doing difference, positive 15,300. I get a pretty big change, negative 20,200 volts. There's been quite a U-turn going on here, right? We've gone from a positive voltage to a negative one, so it's an aggressive change that's going on there. But just kind of pointing out again, because we're doing a difference, right? That's what this Greek letter delta is all about. Because we're doing a difference, we had to do a subtraction in here. Okay, great. So far so good. Now, part B. How much work is required to move an electron from one location to the other? This is really a big, giant conservation of energy equation story. I'm going to see if I can kind of really, in a small way, sneak this in over here. We've got EP plus EK plus work is equal to EP plus EK. There's no heat in these stories at all. And this particular question doesn't have any talk about speeds, so I'm going to throw away the kinetic energies. And I can see it looks like the work is just going to be the difference in potential energies. If I just solve for W there, solve for work, I get the final potential energy minus the initial potential energy. But I can get there by doing this. I can take the Q that we're moving around the electron and just multiply it by the difference in voltage. Because after all, potential energy is just QV, so change in potential energy is Q times the change in V. So this is actually really quick to figure out at this point. I can say, yeah, the work here, let's take our Q, trust the math, negative 1.6, 10 to the negative 19, the elementary charge, that many coulombs. Don't usually put the units in. I'm going to put it in this time. Coulombs multiplied by this difference in voltage. It's almost like a difference in energy. Negative 20,200. I know it's volts, but I'm going to think of that as joules per coulomb. And when we multiply those out, we can see exactly how much difference in energy there is. In other words, how much work is involved. And it ends up being positive 3.24 times 10 to the negative 15. Well, that would be just now straight joules. So we've kind of used this idea, I guess, in the middle of this question that if potential energy is Q times V, then change in potential energy is Q times change in V. So we've used this part A to help us kind of in a nice quick way go through part B. Part C. If a proton was released from location A with a speed, okay, 2.3, 10 to the 2, so 230 meters per second, what's the velocity at B? All right, first thing I want to say about question C, you absolutely must avoid trying to do question C with F equals ma. It doesn't work to try to find the force when you first leave A and then use that with the acceleration that would go with it. The force changes. But that's what energy is all about. That's why we do this whole business of conservation of energy, is to get past this issue. So we've got this same, well, sorry, came out a little funny there. We've got this same conservation of energy idea. Potential energy, kinetic energy, work, potential energy in the end, kinetic energy in the end. In this story, there's no ELF, so I'm going to throw that away. But I do have all the other four terms. There's never any heat in these stories. So we're going to go from A. It's like this side is the A side, and this side is the B side of your story. And we're going to see what we get. So the potential energy at the beginning, right, this EP on the left, that's the potential energy when you're at A. Well, you know, if I just go back up the page here, if you were to put a proton here now at A, it has two energies. There's an energy with Q1 and an energy with Q2. And I've already got that ready to go when I figured out this voltage at A, this 15,300. That's going to help me quickly find this potential energy. Even though there are two energies involved, I can now just go, hey, this is going to be the Q for the proton times that total voltage at A, like just superimposed, plus some speed that you had when you were at A. No work. Okay, the Q for the proton, the total overall voltage at B, and here's where we were really wanting to go, the kinetic energy in the end. So I like this superposition idea. It's putting two potential energies together at once when I go and take my proton, positive 1.6, 10 to the negative 19, multiply it by our positive voltage there of 15,300. That 15,300 packages together both energies. It's a pre-calculation of both of those energies. And then I've got my kinetic energy, 1/2. I'll just grab the mass of a proton off the sheet here, 1.67, 10 to the negative 27. And we were going 230. So that gets squared. Equals, oh, I can't fit this all in one line. Let's just word wrap this around here a little bit. At the end of the day, we have got a potential energy combination at B. No problem. We can put in the Q for our proton, and we have got the combination voltage, negative 4,900. And then here comes the part you want. 1/2 the mass, negative 27, and then the number you wanted, the speed squared. That's going to give you the right answer, right? You have to take the square root, obviously, but that'll give you the right answer for the velocity, and it just deals with the fact that you can't do F net equals ma. Now, before we go to the next page, I want to go back to the top. This question was a bit too much. It's a bit over the top here because it's got not only differences in energy when we took energy at B minus the energy at A, it's also got superposition. It would be incredibly rare to see a question with both voltage difference and superposition in one question. So let's grab another color pen. I'm gonna grab purple or something like that. And I want to show you what this would look like if it was more reasonable. If you were just going to move the electron around from A to B or let the proton fly from A to B, in other words, if Q2 wasn't there, I'm just going to do this all in one color. If Q2 wasn't part of the story, that would be more reasonable. In that case, there's no voltage to superimpose. I wouldn't have to be doing this plus here. I wouldn't have this term or this term. I'd have different values for the 15,000 and the 4,900, but it would probably be more reasonable to see just a Q1 and then going from there. Now, obviously, the numbers for the rest of the page would change, but this is sort of what I would expect. I would expect to see not that, not that, not this, right? So that whole issue is kind of tied together. Okay, I know it's a bit of a mess, but I just wanted to point out that that question's a bit over the top. All right, question number 3. This one is all about fields and forces, and hey, if we're going to do one question and do fields and forces, we might as well do a 2D one, because it can sometimes be like this. So you've got this spot, location X, and there's a Q1 and a mystery Q2 down below you there. They're both 6 meters away, and we're told that there's a total electric field of 625 newtons per coulomb. And the first thing that we're going to try to figure out is, well, how big is this Q2? Well, electric field is all about warning people about force. For example, imagine somebody put a little proton here, right, and you're trying to warn them about what would happen. Well, Q1 being positive would definitely push it away. So, we could create a warning here. We could say, hey, there is a force warning, a field warning, number 1, that's equal to K, the Q value, 2 times 10 to the negative 6. All over, you got to square these ones, 6 squared. That number, by the way, happens to be 500. There's a field, a warning about force of 500 newtons per coulomb. Now, the total is actually more than the 500. It's 625. but you want to resist the urge to go, I guess the other field's 125. It doesn't work that way because this question is two-dimensional. So the other field, imagine a proton going here, the other field would go down. It would be a field this way. When Q2, being negative, attracts something like a positive proton. So the actual superposition of fields would look something like this. 500 for field 1, a mystery field here for field 2, and then a total that goes like this. So this would be your 625. Okay, it's pretty quick to get there. I mean, we can just go and do a quick little bit of Pythagoras here. It looks like 500 squared plus E2 squared is equal to 625 squared. So E2, after we do the Pythagoras, it's not 125. It's actually 375. Okay, now finding out how big Q2 is. It's not that bad. We know for electric field, it's all about a K, the Q you're nearby, divided by R squared. So 375 is equal to the K, which is 9 times 10 to the 9, right? It's on the formula sheet. Q2 we're looking for, and then 6 squared. And so when you're done, you find that this Q it's a 1.5 times 10 to the negative 6 coulombs. But for fields and forces, you typically don't need to put the negatives into the math. You kind of just have to use your head in the end, and now's when you got to look back and go, oh, wait, they told me it was negative. So yeah, okay, it's a negative there. And that downward field adds up with Pythagoras with the across one to make that total of 625. Okay, so far so good. Before we get to the next question, just while that triangle's still in view, I'm just going to go and find the angle there. This is 375. So I'm going to just undo tangent 375 on that triangle. Looks like about a 37-degree angle in there. 37 degrees, I guess, south of east. That 625 newtons that they're talking about, I'm just going to add that. It'll be helpful for where we're going to go in a second. Direction here, 37 degrees south of east for that total field caused by those two Qs. Last question at the bottom of this page says, okay, great. What about the size and the direction for the total force on an electron that might get dropped down at location X? Well, so far we've been talking about putting a positive there. Now they're saying, oh, no, we want to put an electron there. No problem. The force total, well, it's going to be the Q that you want to put there, the electron, multiplied by the electric field total. Now, we don't usually put minuses in for fields and forces, so you just got to remember that you're dealing with an electron. Let's just go with the numbers. 1.6 times 10 to the negative 19 coulombs, and then the total, 675 newtons per coulomb. When you multiply all that out, you end up with 1.0 times 10 to the negative 16 newtons. But here's the catch. The field, the warning about force, was down and to the right. It was south of east. But this was an electron. So this is the moment where you have to intervene. Got to jump in there as a physicist and say, wait, this force is actually 37 degrees the other way. It's actually north of west. It's up and to the left. That's going to happen every time you bring in a negative Q. It's going to go the opposite direction to the force warning. Okay, so we've kind of covered a force field question. We've got a voltage energy question. We've done a parallel plates question. Just kind of mixing stuff up here on the very last page for this one. Got a story about some circular motion. It's a hydrogen atom, and it's got that electron flying around the proton. Most of the mass is in that proton there. The electron's pretty darn light. And there's going to be a force of attraction pulling that electron in. That's why it orbits. That's why it does that circular motion. So I've got my electric force there pulling it in. And we're going to try to find the speed of the electron when it's in orbit. Circular motion, you can't go wrong with good old F net equals ma. So that's what I'm going to do. The force, it's that electric force. So it's going to be Coulomb's law, K, Q for the proton in the center, Q for the electron at the edge, divided by the radius of the orbit squared. That's how far out you're going to be, right? There's some radius going on in there. That's going to equal mass times some version of acceleration. Well, you're looking for speed, so we might as well go v squared divided by r. Now, in orbits with planets, you'd have an m that luckily cancels, but we don't quite have that here. We have an r that cancels, but that's about it. And you can get to k, q, q all over r, which just happens to look a lot like energy, is equal to m v squared, which, by the way, almost looks like kinetic energy. So if we keep going, it looks like the velocity is going to be, after we divide by the m, it's going to be the square root of k, q, q all over an r and an m. So you throw all the numbers in, and by the way, just trivia, just so you know, it's around 2.18 times 10 to the 6 meters per second. Okay. Circular motion, F equals ma, that worked great. Now, this next part is just kind of trivia, kind of almost more setting up for next year than anything else. We're going to try to find the kinetic energy for that electron. We're going to try to find the potential energy for that electron, and we're going to try to find the total energy for that electron just to see what numbers we see. I want to show you that's really similar to what happens with planets. For kinetic energy, you could go 1/2 mv squared. So you could go with 1/2 9.11. We're talking about the electron, -31. You could put in that speed, 2.18 10 to the 6th squared. And it works fine. You get the right answer. The kinetic energy for the electron is 2.2 times 10 to the -18 joules. Potential energy. The exact same thing happens here that happened with planets. The equation for potential energy for charges would be K, Q, Q, all divided by just an R. And by the way, one of these Q's is positive, it's the proton in the center, and the other one is negative. It's the electron flying around the outside. So the answer is going to be a negative answer. If you take a look at what happened back up here, this is just kind of a lucky little deal here. Here's K, Q, Q all over R, right? And you have to go and figure it out. You're trying to figure out K, Q, Q all over R. But this mv squared is actually kind of like 1/2 mv squared, but without the half. It's 2 times too big. So it turns out, just like it does for planets, that the potential energy, it is 2 times as big as the kinetic energy. And it's negative, just like it is for planets. So the kinetic energy, being 2.2 times 10 to the -18, when that's doubled, it means that, sorry, there should be a P. It means that that potential energy is going to be a -4.4. It does the same thing planets do. And then when you total them all up, if we're just going to say, well, total energy would be EK, which is positive and small, plus EP, which is big and negative, well, the EP wins, and you end up with this negative answer, and it's -2.2 times 10 to the -18 joules, just like it was with planets. Same kind of patterning. Last little bit, this is going to help you out with the Unit 7 stuff. Just a little bit of similarities and differences between forces from electric fields and magnetic fields from Chapter 7. Some similarities, they both act on charges. So I'm just going to write that in here. They both act on, let's just abbreviate, they both act on Q's. One of them is nice and simple. It says Fe is equal to QE. Yeah, electric fields will create electric forces. And from our 7th unit, force from magnetic fields is equal to QVB. Yeah, magnetic fields. The differences. Well, I'm just going to split my page here for a little bit. Kind of talk about how they look different. If you take a look at what we did in Chapter 5, F equals QE, that force, contrasting it with magnetic force, that force does not depend on speed. Okay, I'm going to start writing the stuff on the right now. You look at the last unit we did in Physics 12, F equals QVB. For magnetic fields, that one does depend on speed. For F equals QE, the force, it aligns itself, let's just say it lines up with E. Or, okay, worst case, it anti-aligns. You know, if it's a negative Q, the force goes the other way. But at least it's in the same direction. Not with QVB. With QVB, it's three-dimensional. You've got a cross product, what we jokingly call big blue hand, like that big styrofoam hand. Last little thing, if you were to play around with parallel plates and throw particles around inside there, here's what you'd notice. If I make this plate positive and this one negative, and if I was to go inside there and start throwing protons around like footballs, if I gave it some velocity at an angle, I'd find that it actually keeps its velocity in the x direction, but the electric field being down in this story, the electric field would provide a force that's always down, and you'd get a parabola, just like you do with a football. But when you play around with magnetic forces, it's a cross product. It's different. Like if you had a magnetic field going into the page, and if you took a proton, let's start down here. If you took a proton down here and had it move with some speed, if you do your right-hand rule, what you'll find is the force on that is up, and that proton starts to turn up. But then the cross product changes direction, and so does the force, and so does the acceleration, and it doesn't go in a parabola. This one actually goes in a circle. Very, very different. And that's the end for our 5th unit.